Hey guys, another construction here. We are going to be constructing within this triangle the 3 angle bisectors. So this is a construction you already know how to do. We're just going to do it 3 times. So I'm going to start with this bottom right angle, okay? And I am, remember, just creating an arc that goes through both rays, okay? And then essentially I'm bisecting the segment from that. Sorry, slow down. So now I'm putting my pin on this intersection and I need it to be, I'm gonna close mine just a hair. I need it to be a little over halfway, right, to the other intersection point. And so I'm over halfway and then I'm gonna create an arc above and below. The same steps we always do for bisecting. So do arc up here, arc down here, and I'm going to do the other side. So now I'm going to put my pin here. I haven't changed the width at all. And I'm marking here and here. So now connecting those 2 intersection points through the vertex is that angle bisector. Okay, so connect here. And again, we can draw it nice and long. You know you're relatively accurate if those line up well with your vertex. Okay, and we're going to repeat that for all 3 angles. All right, so I'm going to do this bottom left one. So again, this width doesn't matter, it just needs to cross both rays. Okay, and now this intersection point and this intersection point I need to bisect. So I'm going to close mine a little because this one's kind of skinny. So I'm just over halfway there from this intersection to this intersection. And bisect, so below and above. Now move the pin to the other intersection point, right here, and draw those arcs again so they intersect the ones I just did. Okay, those 2 intersection points connect through the vertex. Okay, and one more. And actually, same thing again, you guys. I'm going to go ahead and do all 3. But what we're looking for is the point where all 3 intersect. So I can test my accuracy. I should be intersecting this next one there. Okay, you want it to be as close as you can get. So we're going to bisect this top angle now. So I'm going to turn it upside down just so it's a little easier for me. Okay, bisect here. Oh, I got mine off a little there. All right, so mine's lining up pretty close, so I want that intersection point and those 2 that I just made with the vertex. All right, so this intersection point is another point of concurrency, okay? And this is called the incenter. So 3 angle bisectors in a triangle will always intersect at one point, and we call that, the incenter. Okay, we're actually gonna add one more piece to this one. Our goal is we wanna construct an inscribed circle. So remember the last one we did a circumscribed circle, went around the triangle, we're gonna do inscribed. So what that means is it's gonna sit inside the circle, touching the sides. So what I'm going to do next is I'm gonna construct a perpendicular line from the intersection point, okay? And I'm gonna label these, you guys. I'm gonna call this A, B, C, and then call this intersection D, okay? And so I want to construct a perpendicular line from D to each side. And I'm actually just going to do one side, okay? So I'm going to do it to AC. So we already know how to do this construction. So to make sure that it's perpendicular to AC and goes through D, I need to first open my compass so it's D and just past the segment I want it to be perpendicular to. And then I'm going to create an arc that crosses my line twice. okay? And then I'm gonna bisect kind of that miniature segment. So I gotta close here, intersection, a little over halfway, and do it on the other intersection, not changing the width. All right, so those two intersection points should line up with D if I'm doing this relatively accurately, which that's looking pretty good. Okay, so that line I just constructed is perpendicular to AC and it goes through D. So what I'm going to do now to construct our inscribed circle, oh, I guess I don't need to write the word circle. And again, we could do this for all three sides, right? I could do a perpendicular line from D to BC, D to AB. I'm just going to do one, okay? All right, so inscribed circle. So I want this circle to, I want to use D as my center, and I want it to touch each side. So the reason I created this perpendicular line is because that is the shortest distance from D to this side, is straight down, okay? So I'm going to measure that distance. I'm going to call this point that I just made, where D touches AC, I'm going to call that one E. Okay, so I want to measure the distance from D to E, so I want to match my compass up with that. Okay, and then I want to use that distance as my radius of the circle. So I'm going to keep that distance going, and I'm just turning the page so that I don't adjust my compass on accident, and create our inscribed circle. So those other points where the circle crosses are actually where the other perpendicular lines would fall through, okay? So those distances, I'm gonna label, so we had E, here's F, it's touching over here at G. So that circle creates DG, DF, oh, sorry, I'm putting that on the wrong thing. Maybe I should do color again. So here's, this one just happened to line up with that perpendicular bisector, that's why that one's funky. This one from D to F, and D to E, we constructed that one, so that one's in there. But those are all congruent to each other, okay? All right, so what do we notice down here? That's what we're saying is DE, DF, and DG are all equal. And the reason that makes sense, they are the radii. Radii is just plural for radius. So they are the radii of the inscribed circle. Okay? All right, this relationship that we say the incenter is the same distance away from all the sides of the triangle, that is called the incenter theorem. Okay? All right, so next page here. Again, this is the formal definition of the incenter. This is what it looks like in all the different triangles. So notice it's always inside the triangle in the incenter, and that what helps me remember is it starts with the word in, right? Incenter is inside, and it's the inscribed circle. All those start with the same two letters, okay? So I drew in my circle here, you guys. Again, notice the shortest distance from the incenter to a side is always going to be perpendicular. So I drew those in and labeled them X, Y, Z. So those are all equal according to the incenter theorem. Okay, so let's do a couple problems here. JV and KV are angle bisectors, okay, of this triangle. So that means the point where they intersect is the incenter, okay? Find the distance from V to side KL. So remember, that's always talking about that shortest distance, the perpendicular piece, okay? So that distance is the same to all three sides. So this one, and this one, okay? Well, that one's given to me as 7.3, but I know all three of those are going to be the same. So this one is also 7.3. Okay, angle VKL. And sorry, I kind of covered that one up. That says 106. All right, VKL. So they want this angle here. Okay, well, these are angle bisectors, so I know those angles are the same, and these angles are the same. So this one is also 19 degrees. So I have 19 plus 19 is 38. 38 plus 106 is 144, okay? And so to get angle K, I'm going to do 180 minus 144. So this is the measure of angle K, which I get 36, okay? Now, VKL is half of that. This angle is being bisected. So measure of angle VKL is half of 36, which is 18 degrees. So again, using the theorem, but also just using our definition of bisect. And triangle sum theorem in this case. Okay, here I'm told P is the incenter of the triangle below. Given PX is 3x plus 24, BP is, okay, so they're giving me a bunch of information here. They want me to find AX. Leave your answer in exact form. Okay, so all of these expressions involve X, right? So it'd be obviously helpful if I knew what X was. So the only thing I know about this triangle, based on that P is the incenter, is that those three distances are equal by the incenter theorem. So one way I could find X is set two of those equal to each other and solve for X. So all that extra stuff I might not need, okay? So I'm gonna look for PY, PZ, or PX. So there's PX, nope, nope. Here's PZ. Okay, so those two are equal to each other by the incenter theorem. So I'm gonna set those equal so that I can figure out what X is. Okay, so I'm gonna get my X's together first. So I have 24 equals 3x plus 9, subtract 9. So I get 15 equals 3x, divide by 3. So x is equal to 5. Now remember, they wanted me to find ax. So ax is this distance, and it doesn't look like they give me any information for ax. So I'm going to see AX is part of this right triangle, so let's see if I know anything else. Do I know these two sides? So I'm actually going to blow this up a little bit, you guys. So I have A, X, and P. We are looking for this side, okay? PX, well, PX I had right here. So PX, I know X is 5, so 3 times 5 plus 24. So let's see, we got 15 plus 24 is 39. So PX is 39. AP, I also had an expression for, or PA. So 7 times X, or 7 times 5 plus 10. So 35 plus 10 is 45. Okay, so now I can do Pythagorean theorem. So we'll call this side little a. So I can do a squared plus b squared equals c squared. And I'm making sure I'm putting 45 in for c. Okay, so I'm going to use my calculator here now. So I have 39 squared. So I have a squared plus 1521 equals 45 squared. 2025. Subtract the 1521 from both sides. So I have a squared equals 504. I don't think that's a perfect square, but I'm going to check. Nope, not a perfect square. So I want to see, can I break down the square root of 504? So I'm going to do some division here. Let's see. Oh, okay, so 504, 9 goes into it evenly. So I'm going to do a little breakdown. I'm going to do this off to the side. So 504 is 9 times 56. 56 is the same as 7 times 8. 9, I can do 3 times 3. There's a buddy I can pull out. 8, 4 and 2. 4, 2 and 2. So I have a 3 and a 2 I can pull out front. So 3 times 2. Underneath I still have a 7 and a 2. So our A, which is actually, I'm going to relabel side AX, is 6 times the square root of 14. All right. Okay, that's all for this video, guys. Thanks for watching.